So now this is the third lesson of my short introduction to antennas for space applications. In the previous lessons we looked into some basic principles related to antennas in general. In the second lesson we looked at the specific applications of the general principles of antennas to onboard applications, application of satellite antennas for satellite communication or other type of applications, and we looked also into some basic configurations, for instance reflector antennas and direct radiating arrays and active antennas. Now in this third lesson we will look at some real application of antennas on board satellites. Also we look at some components for antennas, and then we will touch upon the matter of satellite antenna testing, defining also terms such as near and far field of an antenna, and we look at the end at some specific antennas meant for a generation of micro, nano and pico satellites, which have some peculiar type of characteristics and needs. So let's start with the real antennas that were used in the past and are still used in orbiting satellites. I will not describe them all into detail. So there are, in this slide you see, for instance, several antennas that have been used on INTELSAT satellites. Just to mention, well, you see that first of all the complexity of the different configurations. You can also imagine all the complexity of the technologies involved. Some of the structures, the mechanical structure you see, are most of the times using carbon fiber to make the antennas very stiff, but at the same time also very lightweight. You see the complexity of the geometries of the antennas. You can also recognize, for instance, if you look at the antenna at the bottom, the second antenna from the left, the INTELSAT 8 antenna, you recognize a double reflector type of configuration, for a Gregorian type of configuration that we looked at in lesson 2. As you recognize in the simpler offset fed reflector, single reflector, INTELSAT 6 is the second top from the left. So there are different types of configurations. They were all the configurations we looked at in lesson 2 are more or less here described, and you see that there are good reasons why one configuration or the other was used, and many times it depends on the type of application, but also the accommodation on satellites. If we look at the following slide, we see an example of antenna farm. Antenna farm meaning the number of antennas that compose the overall payload of a satellite. So we see at the top on the left the Olympus, a rather old satellite made by the European Space Agency, antenna farm. And we have some other examples of antennas with some feeds. At the bottom we have antennas working at dual frequency 20-44 GHz in double reflector configuration. On the bottom right side we have a SIGRAL antenna, also a satellite for military application, which is instead a single offset antenna, offset in an offset type of configuration. So many type of antennas, different type of accommodation, different type of requirements, different frequencies. Every time the best configuration is realized and studied and analyzed. Every solution fits the particular requirements, mechanical accommodation and electrical requirements of the specific mission. The following slide is also depicting some real antennas from very sophisticated and advanced and demanding remote sensing and scientific missions. The first two antennas at the top of the slide, the ERS1 and ERS2, you see that in terms of configuration they are center-fed reflector type of single reflector antennas. They were both used on ERS1 and ERS2, were altimeter type of satellites with as antennas for the radar payload of the satellite. On the bottom and on the right side of this slide, you see a very, very advanced and then sophisticated and complex multi-frequency, multi-band antenna for the Cassini mission, to Saturn. That was a joint venture between NASA, ESA and the Italian Space Agency. This antenna is a very large reflector, 4 meters in diameter, working at different frequencies, and it had to stand very severe constraints, because we never mention it, but it's obvious that this type of antenna poses very challenging problems in terms of mechanical design and environmental constraints. Think of the environment of space, where one side of the spacecraft can be at -200. When you look at the deep space, in fact, you can reach temperatures very close to the 0 Kelvin, that is the minimum temperature you can think of. Typical temperature for the dark side of a spacecraft can be easily -200 degrees. When you are illuminated by the sun, temperature can raise up to plus 200 degrees. So sometimes the antennas have to survive into temperature ranges between -200 and easily plus 200. This is just an example. Of course, they have to stand all the stress of the launch phase, to stand also all the problems related to the space environment, such as radiation, the accumulation of electrostatic charges. So this is a good reason why antennas have to be grounded, to avoid that such large reflectors collect electrical charges and create problems in terms of discharge of this accumulation of electrostatic charges, creating problems to the rest of the spacecraft. So there are several problems associated. To make such a big antenna able to reach the far sides of the solar system, working at different frequencies. And by the way, this antenna is guaranteeing the connection of the mission to ground, to the Earth, over the complete duration of the mission itself. So this type of design are very complex, and they require very sophisticated techniques, both for the electrical design and the mechanical design. The following slide is concentrated on examples of feed elements. These are the part of the antenna these are apertures, if you want. Most of them here are circular apertures, but for the one at the bottom on the right side, where the rectangular horns, these small apertures are usually called horn. They can be circular or rectangular. And those are these apertures are the one connecting on one side to the communication payload, either receive or transmit side, and they illuminate the reflector, either the sub-reflector or the main reflector, depending on the type of configuration. These are called feed assemblies, let's say. Feed element, because they might be single element, or they might in fact put together several elements, as we saw for instance, for shaped antennas. And we also mentioned already the need for beamforming networks. Beamforming networks being networks where you divide the signal and you feed an array of feed elements with proper amplitude and phases, with the objective of creating either a multi-spot type of coverage, or to combining several spots together to create what a shaded and or well-contoured beam over the area to be illuminated by the antenna. In the next slide, we see the realization of large reflectors. Up to a certain dimensions, these reflectors can be made of with a solid design, in this case carbon fiber, which is very light, but still strong enough to survive the stress of a satellite launch and mission. And this was a reflector with 4 diameters in diameter, so in order to accommodate the reflector on the spacecraft, it was conceived with foldable tips. So this was somehow reducing the dimension. But other type of reflectors, larger also in diameter, were designed and then realized. Here there is one example of a reflector that was developed between a company in Italy and a company in Georgia, and it is an unfurlable reflector that was actually tested experimentally on board the Russian Mir station. But similar reflectors have been already realized. Now they are flying, they reach diameter up to 10 meters and above. So those are the reflectors that were mentioned in a previous lesson, able to generate a very fine coverage of the Earth with small, very small spot beams. And those spot beams with a very high gain, because I remember to myself and to you that narrow spot beams, so narrow beam widths, correspond to high directivities, high gain over the coverage. Those spot beams allow the use of a very simple terminal that can be portable. So it's no longer needed a large reflector, not even the small reflector we use for TV broadcasting, but we can even realize satellite communications to individual users with sort of smartphones through the adoption of very large reflector antennas. And these large reflector antennas, of course, cannot be deployed before launch because they would be too large to accommodate any launcher. So they have to be sort of the umbrella type. One word to name this antenna is a sort of umbrella antenna or umbrella reflector, and they are also defined unfurlable, in the sense that with the principle of different type of mechanism, when they are stowed, they look very small, rather small cylinders, and when they open, of course, the reflecting surface now is a mesh. It's a metallic mesh. It's no longer rigid. It's really like a tissue, but made out of thin wires. Usually these thin wires are gold-plated in order not to create problems of oxidation, at the same time being a very good reflective surface. The surface is good enough. It depends on the frequency of operation, of course. The higher the frequency, the denser has to be the mesh that is used as a reflector. There are also, we mentioned them in the second lesson, array antennas that do not need a reflector, and they are more or less direct radiating. There are several examples, some examples on the top of the slide of arrays of slotted waveguides, so a waveguide type of technology, but at the end the principle is that the aperture of the antenna is composed of individual elements, and those elements radiating in the same signal in a proper way create and sort of sample the aperture and create a beam that is somehow equivalent to the beam that would have been generated by the full aperture. We have already mentioned the array of microstrip patches used for Galileo as a navigation antenna, as a transmit navigation antenna. And at the bottom we see an example of a direct radiating array of patches used by the military satellite, Italian military satellite SIGRA at the UHF. Here the patches are very big because you can imagine frequency is relatively low and the patches are very huge in terms of dimension. The overall array is very big, but the principle is the same, used at higher frequencies in a smaller dimension. And finally, at the bottom, on the right side, we see the array of, there are two arrays, in fact, one is more visible, the other is less obvious to recognize, but the circular arrays used on board the Mediosat satellites up to the second generation. The second generation is the presently flying. Those are the satellites that get the pictures of the Earth with all the evolution of the meteorological situation. We use it and we look at it, at those images every day on TV, for instance. And being the satellite spinned type of satellites, so they rotate around one axis, the antennas in this case are used to counter spin. They are so-called D-span antennas, so antennas that create a beam that is rotated to compensate for the rotation of the satellites, and they keep being pointed always toward the Earth, while the satellites itself would rotate on an axis, and so without this array of elements, the beam itself would rotate solidal to the satellite. It would not guarantee the fixed coverage over the Earth. Now, so we saw that antennas can be very different. Of course, there is a problem about the testing, how to test an antenna. We spoke about the antenna as an interface between a guided wave and a transmitted wave, a planar wave transmitting and traveling in space, freely in space. And this is true, but oversimplifying, we forgot maybe, or we just mentioned the fact that between the antenna and the far field generated by the antenna, there is a sort of intermediate region. As a matter of fact, we can define two intermediate regions where if you want, the field of the traveling antenna is not fully created. So in fact, we call this intermediate region in general as a near field of the antenna. Then we could distinguish between a non-radiative or reactive and radiative near field, but for the sake of this course, it's enough to understand that up to a certain distance from the antenna, the plane wave is not well created. Plane wave not being created means that the assumption that the electric field and the magnetic field are orthogonal to each other, and then orthogonal, they stay on the same plane, orthogonal to the direction of propagation, is not completely true. After a certain distance from the antenna, this is true, and we have created somehow the plane wave that is traveling and then goes on till the end of the universe if nothing stops it. The separation between the near field and the far field is approximately fixed by the formula that is shown in the slide, is 2 by d squared over lambda. D not being directivity, unfortunately the same symbol sometimes is used for different quantities. In this case is the maximum linear dimension of the antenna. It's important not to confuse with directivity. So why are we defining near and far fields? Because we need to decide how to test the antenna. And the most obvious choice would be to test the antenna in the far field, because this is what we are interested in. We want to see what is the pattern of the antenna in the far field. That pattern would be the same 1 kilometer from the antenna, 10 kilometers, 1,000 kilometers, or 1 million of kilometers from the antenna. That is the real far field pattern of the antenna. So the simplest and most obvious way to test the antenna would be to test it into the far field. We'll see that there are other techniques, but it's important anyway, depending on the choice of the approach, to know where the far field of the antenna is. And the far field starts depending on the frequency of operation through lambda and the size of the antenna. Very well. Having said that, as we said, we can test in far field, so we need to be far away from the antenna. Then we need what are called the outdoor test range facilities. Outdoor because if you want to realize, for instance, a distance of several hundred meters from your antenna to the other end of the test range, so you put your antenna on one side and, for instance, you transmit, and then you have some 100 meters away a receiving antenna, and then you, through that receiving antenna, you sample the beam of the antenna, you derive the pattern of the antenna. This range cannot be indoor. This can be a problem for satellite antennas because satellite antennas have to be realized under certain quality conditions, so the outdoor environment can be dangerous, so you have to be careful, so you have to put, maybe realize some protections. You see that there were sort of balloons transparent to the electromagnetic field. But this approach is still theoretically the most valid because you are really testing the antenna in the actual operating condition. You are far away from the antenna. You can assume that what you measure is really the far field of the antenna. There are other cases where you want to test antennas indoor because there you have a better control of the situation. This can be easily feasible, for instance, for small antennas, because we saw before that the smaller the antenna, the closer is the separation between a near field and far field. So for a small antenna or an antenna that works at very high frequencies, so although being small in physical terms is not small if compared to the frequency and the wavelength of operation, then you can still afford to test these antennas indoor. Then you have a chamber that is called anechoic chamber, in the sense that you have tried to avoid the reflections from the walls of the chamber. So the chamber simulates open space, and you can inside this put your test range and derive your radiating pattern. Indoor facilities are also used for all the components related to the antennas, to make many tests that are related to the realization of the overall antenna assembly.